Well, this is a very, I mean, I think of most people, there's not very many people here, so I'll just make it quite quick then, really. So, what I'm going to talk about is, so here at Chipflow, we've been basically developing a platform to making chips easier and faster, and make it easier for, hardware manufacturers to be able to make their own custom chips. And we're heavily leveraging and contributing to multiple open source projects as part of building that. And what I'm going to talk about today is kind of like a trial experience, I'd say, that we had building a chip for a particular use case within a car, an automotive use case. And this was done with an actual well-known car manufacturer who you'll know, but I can't tell you. And so, basically, it took a while to get this project started. So by the time we kind of had got to the point of starting to collect requirements, the next tape-out deadline was in 3 months' time. And I think for most companies that design chips or do custom chip design, that would be a ridiculous thing to try and do, right? So we thought we'd do it because we like doing things that are ridiculous. And one of the big needs that this customer had is, if you look at a modern car, there's probably like 140 processors in there. Each one's running a completely different piece of software from a completely different supplier. And yeah, can you imagine managing like the software distribution load? This is why for most cars you don't get updates, because how do you do that? And so they really wanted to have systems, start investigating how they could start changing their architecture to reduce that software load or centralize it more. And this is a very big theme across automotive. And so, okay, we've been building this platform. This is a really good chance for us to find out, does our platform actually help us? This is a situation we want to be able to support, enable companies to deal with. Does our platform help? So what we've built there really is a VS Code and Python development environment. It comes with very deep debugging. You can get full traces of everything that's going on in your design. Put breakpoints on, put breakpoints in software, have that trigger a hardware breakpoint, etc. And then in the background, we've got a cloud system which will take a design and build that into an actual, what we call a GDS, the input to a foundry to make the chip. And we've built up a set of partners, of chip manufacturers, foundries. And I think, trying to think which ones I can talk about. Some well-known ones, I'd say. And then the partners which do the testing of the chips and the packaging of the chips, which is, chips are a very small piece of silicon. When you see them on computer motherboards, they're in a little plastic package usually, legs, and that's called a package. And just doing that bit's quite complicated, right? So we got all that kind of automated out with all the partners already in place. There's still lots of, funky corner cases you hit all the time, but that's there. So here's our little. So there's an open source project. It's called RTL Debugger. I should have put a link there, but if you search RTL Debugger on GitHub, you will find it. So we can dig in, really see what's going on in the design. We can get starting to be able to get high-level tracing out of it, so you can actually get a high-level understanding of how your design's working. And you can see here, you can see all the components within the design and all the wires and all those components, and that's kind of always there for you to dig in and see how everything's behaving. And this is what it looks like when you click. So there's actually a command line tool which you can use to send this to the cloud, or you can plug it into your CI system, which is what we recommend. So you're constantly always testing how this is going to tape out on real silicon. and that's done with our cloud platform. And so kind of what we've built there really is something that makes chip design a lot more like software design, right? Which meant that we could take, because the traditional way in silicon is, you spend 3-6 months collecting requirements, then you get agreement on that because, then it takes a lot to turn those requirements into actual designs. And then you've got to manufacture that. That's going to cost you some money. Then you've got to test that. That's going to cost you some money. So there's a very big period of just collecting requirements before, and then you go off and you do design, and then you go and build your test chips, then you test that, and then you iterate, and then get to manufacturing. So, generally building a chip is going to be at least a 3-year project, right? But because we've built this more software-like environment, we can kind of start executing on a more iterative requirements to design iterative model, right? So what we're doing, and this kind of feeds into the automotive side as well, because I'll talk about it in a little bit, about the requirement, safety requirements in automotive. So you definitely have to capture your requirements because they are what determine whether you're doing something safely at the end of the day. And so, so we got an open source model as well for the requirements capture, and then allows us to iterate between them, and basically kind of have something that we always know where we are against the requirement set. We always know what's fully tested, right? We know the coverage of the testing. So you can kind of go take a bit at a time and move out, and also be reactive to, a lot of the companies we're working with haven't built a chip before, right? So you get halfway through and you kind of like maybe get an FPGA demonstrator together for them to test in a real world situation. And then they go, oh gosh, yeah, this should have happened like that. This should have happened like that, right? And so this gives us a way to really kind of give that interactive relationship between customer and design. So we did this anyway, yeah. We went from starting to collect requirements to actually making a tape out. And we did this on Global Foundries, the 130 nanometer process, 130 BCD, which is an automotive grade process. And we sponsored Precision Innovations, who are kind of the main contributors to OpenRoad, an open source tool for doing chip layout, and also did some work ourselves to kind of enable that within that. That wasn't actually too bad. There was a few things, like there's just, like what you find when you're actually working with the actual foundries is every foundry does some weird things, different things in weird ways, right? And there are things that trip you up. And I think it was fill rules, like local fill rules or something like that. If anyone knows anything about chips. If you're not, talk to me later. I'm not going to explain them here. But yeah, a few things like that, which kind of just meant we were still hacking like the layout engine like a few days before delivery, before we had to send the GDS off to the foundry. But we got there. And then functional safety, right? So this is the biggest challenge that I think this is going to be a really multi-year challenge as well to do this properly, right? There are, the kind of a big standard in automotive called ISO 26262. There are also kind of similar but different functional safety standards for medical devices and aerospace. You name it. They're all the same sort of thing, though, right? They are know what you're building, figure out where things can go wrong in what you're building, and make sure you specify and then handle the way things could go wrong. So either you're kind of doing design so it can't go wrong, or you're finding out, you can't do that, so you've got a mitigation strategy, right? And you're generally looking at it whether, is it that, if this goes wrong, the car stops moving, right? It's a little bit of that's a bit of a safety issue, right? But it's not like, So yeah, so if the car stopped moving suddenly or turned to the left and swerved into a wall, that would be a very hard. That'd be a what we call a B level issue. And you might have other things like more like a D level issue, like my interior lights are the wrong level, right? It goes dark in the interior of the car when it's not supposed to. That is a safety issue, but it's not like going to kill anyone. So you got to go through your use cases, and the hard bit here is really those use cases are not at the chip level, right? Those use cases are at the car level, right? And how this is being used. A security element out of context is what this is called. And so you've got to know what requirements pertain to you. You're going to map them, and you want to have a mapped requirement structure that allows you to then know that you're fulfilling your requirements, and also that you can find the safety issues that can be hit. And so, yeah, we've been working with an open source project called Doorstop for this. And actually, I just saw yesterday that an old company of mine, CodeThink, has just released a suite around this sort of area as well. So looking forward to dig into that. But they also use Doorstop as well. So that's, yeah, kind of an interesting area. And so where do we get to? So what we managed to do was actually quite impressive. So the use case we looked at was a door, and in a relatively high-end car. Like, what's the electronics needed in the door? And it was surprising. There were actually, I think, 4 different suppliers involved in the software and logic and hardware for the door behavior. And I think it was 11 processors, if I remember correctly. So what we managed to do is take all of that and reduce it down to one chip with one safety surface, and also kind of move to kind of a modern architecture by supporting Ethernet T1S. So in about 3 months, and a cost. So this is full NRE and tape out of about 300K. So this is a really, really great test case of what we've been trying to build. And this has led on to further engagements in the automotive space, which I hope I'll be able to get to talk about. Maybe this time next year, we'll see. But that's everything from my talk today. So questions? Thank you, everyone. No questions? Oh, go. I'll bring the mic over to you.
Yeah, I think this is really cool. One thing I was wondering, so I think it's really cool to have the kind of more software-like way of doing hardware. How do you deal with what you were already mentioning a little bit of the stuff that you can't really describe in the main language, like I guess all the like analog IP and things that the Foundry adds, that kind of stuff. Like how do you deal with all of that? And yeah, your thoughts on, because that's essentially like you could do a lot of things in like, I guess, simulation and all that kind of stuff, but the stuff that you always trip up on with your test chip is all the stuff that was added after that.
Yes. Oh God, 100%, right. Yeah, so at the moment what we're doing in our process is just kind of having very fixed function analog blocks that, you know, we're buying in, are well tested, are well understood. But yeah, these and the integration of the analog block into the digital design, in the layout, that's actually automated. But my general feeling on all of this is the more that we can have higher level machine readable specifications, the better this can be, right? And also going back to the previous talk, the more we can apply Gen AI to helping us build better, right? And faster. So yeah, so there's going to be so in the EU there is now a $60 million euro funding pot for open source chips, which has to be matched, I think, as well. So about that. And there's going to be a thread in there looking at generative analog design, so you can have higher level analog descriptions and then generate the actual physical design based off, the end requirements, right? So that's going to help a lot with that, and that'll help us also then have in Python you can start describing it, or in higher level language. And part of how we're dealing with kind of like the stuff that gets added after, your 80, I'll not use really complicated terms, but your test infrastructure and that sort of thing. Really, the aim there is to have as minimal a difference between customers as possible, right? So that is a standardized thing that we know how it works, and how it works is driven as much by the customer design as possible. That makes sense? Any other questions? No? Okay, thank you very much, everyone.